Alright, for problem number 19, we're asked to find the limit of a particular function x minus 1 over x squared minus 1. Okay. Problem is, when I plug in 1 for x, my denominator will go to 0. Now, if I graph this on a graphing calculator, we could probably get the limit by looking at it as we approach from negative and positive infinity. And so that was the first step, but we were asked in the textbook to confirm this algebraically, and I'll show you guys how to do that in a second. So let's graph this bad boy. X minus 1. Oops. X minus 1 divided by the quantity x squared minus 1, and we'll hit graph. And so what we're looking at is as x approaches 1, so what I'm going to do is if I hit trace and I come in from negative infinity, as x gets closer to 1, I want to see what my y value approaches. It should be 0, right? So let's look again as I get closer to 1. Oh no, it shouldn't be 0. Let's zoom in and see what we get. Zoom in. And so I'm gonna, well, let's set the window. Let's do from like 0 to 2. Whoops, 0. So we'll do 0 to 2 for the x window. And for y, we saw that it was positive by looking at the graph. So I'm going to do like 0 to 2. Okay. Hit the graph and we'll zoom in on it. Alright, so see this little blip here? See this little hole? That's at x equals 1. Alright, so if I hit trace here and I come a little bit from this side, okay, so I'm coming from negative infinity, right? I'm coming from the left. As I get closer and closer and closer, I don't know, it looks like 0.5 maybe? In other words, as this number gets closer and closer to 1, this one gets closer and closer to 0.5. Okay? So, one more time. So, see here, I'm almost at 1 and this is almost at 0.5. Now, if I were to come in from the other side, in other words, if I were coming from the positive infinity or the x positive infinity, it looks like that it's getting close to 5 as well. Okay? So as this number lowers towards 1, this one gets higher towards 0.5. See how that works? But it's undefined at 1. So how do I do that algebraically? How do I prove it looks like it's 1/2? Well, what I could do is I could think about, and you'll get used to this, you'll do this automatically, x minus 1 on the top, but isn't this a difference of squares? Isn't it the same as x plus 1 times x minus 1? Hey, wait a minute. I've got an x minus 1 on the bottom and an x minus, or 1 on the top. I could reduce that. Okay? So if I reduce that, I literally have 1 over x plus 1. And if I plug the 1 in now, I get 1 over 2. Okay? See what I've got there? So I've shown algebraically, but I want to make this perfectly clear. Here, this is the limit of 1 over x plus 1, which is the same as the limit of this, which is 1/2. But this function and this function, they're two different functions. And let me show you what I mean by that. If I pull up the graphing calculator, this is a function, x minus 1 all over x squared minus 1. However, if I go into my grapher here and I type in 1 divided by the quantity x plus 1 and I graph that, it fills in the gap. It plugs the hole. So let me show you something else that's really cool. If I take and I plug in 1 for x, here it's undefined. Why? Because we're using this equation. But if I scroll down and use another equation, it's defined. So the reason this works algebraically, truthfully, is that this function here goes on top of the other function. It kind of goes over it. It covers it up. So graphically speaking, they look almost exactly the same, except one plugs the hole at x equals 1 and the other one does not. So if I were to go up or down, I was trying to show you something and I got a little crazy there. So if I hit trace and I plug in 1, that's that function, not defined at 1. This function is defined at 1. Okay? Another way to look at that, and I'll draw it on the paper and then I'll stop talking about it. Graphically, what we're doing is this. If I were to graph x minus 1 all over x squared minus 1, this is a function here. It's going to look something like this. But when I get to 1, it's not going to be defined. Actually, it's more like down here, right? It looks more like this because it's at 1/2. Okay, so it's not defined when x equals 1. In other words, if I take this function, f of 1 is not defined. There is no, it doesn't exist. Okay, there is no value. It doesn't have a value. I can't. It's undefined. However, if I come in and I graph g of x, which is 1 over x plus 1, I'm simply graphing right on top of the other. And that's how it works. Oh, g of x, not f of x. So if I say g of 1, that equals 0.5. Does that make sense? That's how that works. So a lot of times in calculus, what we want to do is we'll look at a function like this. We can't plug in 1 because there's a domain restriction. In other words, in this particular case, the domain is all real numbers except x equals 1. So I can't do it by substituting the value 1 in for my limit. So what I'm going to do is I'm going to algebraically see if I could factor the top and factor the bottom, see if it simplifies to what we call an equivalent or sort of equivalent function. And then that function, we should be able to obtain a limit on it. And if this function is going to go on top of this function, where this one is defined and we could see what the limit is going to be of this one, then I can only assume that the limit would be the same for this one. So what that looks like graphically is on my original function, if I go to graph it, I can still find the limit by looking at the graph, because as I approach from negative infinity, right, this is the negative infinity side of the x-axis, this is positive infinity. So if I approach from here, it looks like it's approaching 0.5. If I approach from here, it looks like it's approaching 0.5, right? But I can't prove that one algebraically. So what I do is I create that second function, graph that, and it's defined right here at 0.5, right? So this is 1 comma 0.5. And so I can now algebraically confirm through the use of another function that it does have a limit of 0.5 or 1/2. Okay?